Welcome to the 25th lecture of graph theory. So, in the last class we were looking at several classes of perfect graphs. Now, let us ask the other question. Can you think of some non-perfect graphs, graphs which are not perfect? So, after some thought, everybody will come up with the following example: odd cycles of length 5, at least 5. Why are they not perfect? Because see, if we consider an odd cycle, so then how many colors are required? So, this is an odd cycle, right? How many colors are required to color it? Chi of g is equal to n by 2 seal, right. So, for instance, if it is 7, we need 3 here. Now, omega of g is equal to 2 on, sorry, the not n by 2, the for to color the odd cycle we need 3 colors, right. So, omega of g is equal to 2 only. Therefore, chi is strictly greater than omega. So, for odd cycles are not going to be odd cycles of length 5 or more, 5, 7, 9 like that are not perfect, because the chi is strictly greater than omega there. See, odd cycle of length 3 is not an example, because here 3 colors are required to color it, and also the chromatic number is equal to 3 here. So, therefore, they are not examples. Now, so they, of course, obviously we will look at the complement of it. They are also examples of non-perfect graphs. Why are the complements of an odd cycle, say for instance is an odd cycle, and you can consider the graph which is complement of it. So, like this graph, right, the red, the graph defined by the red edges. This graph. So, is it okay here also? Okay, this complement graph. Why is it an example of a non-perfect graph? So, for instance, if you try to color this chromatic number, that will become the clique cover number for the cycle, and because there are 2 vertices in a clique. So, we need how many cliques? It is essentially n by 2 seal cliques are required. So, therefore, clique cover number is of the cycle is n by 2, and we know that, yeah. So, the chromatic number of the complement is going to be n by 2. On the other hand, if you look at the clique number of this omega for this graph, that will happen to be the alpha of the cycle, and that we know that n by 2, that is n by 2 floor only, right. For instance, if in a 7 node graph you could have taken this vertex, and this vertex, and then you can take this or this, right. Only 3 you can take for 7. So, alpha. So, here alpha is strictly less than clique cover number, that is the chromatic number of the complement is strictly greater than the omega of the complement. So, these 2 graphs are the typical non-perfect graphs. They are the obvious examples of non-perfect graphs. Are there other examples? Of course, there are other examples, like you can take a odd cycle, right. You can take an odd cycle of length 5 or more and add something like this. It is non-perfect. Why is it non-perfect? Because this odd cycle is there as an induced subgraph in it, and of course, this induced subgraph will not satisfy the chromatic number is equal to clique number condition, right, for this subgraph, because you remember the perfect graph requires that for a graph to be perfect, we require that every induced subgraph satisfy the chi equal to omega condition. Every induced subgraph satisfies the chi equal to omega condition. So, this brings us to this question of what are the minimal imperfect graphs, because that induced subgraph if you take. So, you can always ask, okay, this is an perfect graph, this is a non-perfect graph, okay, there should be some induced subgraph which violates the perfectness condition. So, you pick up that induced subgraph, you can look into even further, like you can ask, okay, why is this imperfect, is it because of some induced subgraph, and then go for the smallest induced subgraphs. So, the minimal imperfect graphs, in the sense that if you take any induced subgraph of it, the condition is satisfied, but for this graph it is not satisfied, right. So, for instance, the cycles are odd cycles and its complements are one such case. If you take any induced subgraph of these odd cycles, then they satisfy the chi equal to omega condition, while this graph itself does not satisfy the chi equal to omega condition. Therefore, see, interesting thing is, okay, once you see these are the two minimal imperfect graphs, and then are there other minimal imperfect graphs. So, Birch conjectured that, this is what we are saying, Birch conjectured that a graph is perfect if and only if it has no induced Hall or anti-Hall in it. Anti-Hall means the complement of the, and Hall means an induced cycle of length 5 or induced odd cycle of length 5 or more, right. And anti-Hall means the induced cycle of length, the complement of the induced cycle of length 5, 7 or 9, right, the Hall and anti-Hall. So, here maybe you can say odd Hall or odd anti-Hall, or maybe it depends on the author. So, the graph is so that he conjectured that any imperfect graph should contain as an induced subgraph an induced cycle of length odd induced cycle of length 5 or more, that is 5, 7, 9 like that, or the complement of it. One of the two things are required, right. This was his conjecture. Then of course, it was a difficult conjecture, somehow nobody could prove it for a long time, and then very recently in 2002, Chudnowski, Robertson and Seymour and Thomas, they proved the conjecture. They say that a graph G is perfect if and only if neither G nor G bar contains an odd cycle of length at least 5 as an induced subgraph. Or equivalently, it is like saying that G does not contain a Hall or an anti-Hall. That means, it does not have a odd induced cycle of length 5, or it does not have a the complement of the induced cycle of length 5 or more, or equivalently it is told like this. So, it is either G or G's complement does not contain in induced cycle of length 5 or more. This is what it is known as the strong perfect graph theorem. Historically, there was a weak perfect graph conjecture also, which was proved by Lavash. So, which said that if G is a perfect graph, then its complement is also a perfect graph. We have been verifying this for several graph classes in the beginning, and then whenever we saw that a graph class is perfect, we saw that its complement class is also perfect, right. Now, that is a general statement. In fact, whenever G is perfect, G complement is also going to be perfect. You see, once the strong perfect graph theorem is known, that means this statement, that if G is perfect if and only if neither G nor G bar contains an odd cycle of length at least 5 as an induced subgraph. So, it is clear that if G is perfect, G bar is also perfect, because when G is perfect, G does not contain an odd induced cycle, G bar also does not contain an odd induced cycle, and the statement is symmetric for G complement, right. So, it also does not, if G bar is equal to H, H and H bar will not contain odd induced cycles, right, is not it. So, so that will follow from that, but again the proof of the strong perfect graph theorem by Chudnowski, Robertson, Seymour and Thomas is too long, and also it cannot be taught in a class. Therefore, we will to get some very nice intuitions about this perfect graph and to appreciate the beauty of this perfect graph topic. It is a good idea to look at the weak perfect graph theorem, namely the graph is perfect if and only if its complement is perfect, and it is proved by Lowash and its shorter proof by Gasparian. That is what we will aim to do in this class, right. So, now our intention is to look at this one. So, to do that we need some lemma which is developed by Lowash. So, it says a graph obtained from a perfect graph by expanding a vertex is again perfect. What do we mean by that? So, first of all we have this operation called expanding a vertex. Suppose you have a graph here G, and then suppose this vertex, this is the vertex of the graph, these are the neighbors. Then I say that this is x, this is expanded to an edge x dash. So, you introduce a new vertex x dash, you connect it to this, and also you connect this new vertex to all the neighbors of x. In other words, x is some kind of a copy of x dash is some kind of a copy of x, in the sense that it is connected to exactly the same set of neighbors as x, and also it is connected to x. This is called the expansion operation. So, you can see that you can keep on expanding. For instance, you can suppose now if I expand again with an x double dash, what will happen? So, it will be connected to this, now it will be connected to all the neighbors. So, here including x dash. Now, as you keep on expanding, here you will get a clique which is connected to the same set of neighbors, and so a clique such that all the vertices in it is connected to the same set of neighbors. This is what will happen when we expand a vertex. So, the lemma says if you have a graph perfect graph G, this is a perfect graph G, and then you select some vertex x. Now, you expand it to an edge by adding a new vertex x dash. That means, this is the situation, these are the neighbors and this is connected to this. Okay. So, if this is what we are going to do, then we will, this lemma says, so let this new graph be called G dash after expanding. So, G dash is obtained from G by expanding the vertex x to x dash, the edge x, new vertex x introduced, and x dash is made adjacent to x and made adjacent to all the neighbors of x. So, now we will say that G dash is also perfect. We want to prove that G dash is also perfect after expanding. Whatever graph you obtain is also perfect. How do we prove it? So, we will prove it by induction. So, for instance, if it is a one node graph, G was a one node graph, then there is nothing to prove. It's because expanding will give you an edge and then it is perfect. There is nothing to be proved, and then small, even for two node graphs you can easily verify that it is the perfection. So, therefore, let us inductively assume that if for all smaller graphs the theorem is proved, whenever you expand a vertex the perfection is not lost, the property of being perfect is not lost. Now, you take a new graph, n node graph, and you identify the vertex x, and now you are expanding it to x dash, right. The question is, so here these are the neighbors, right, these are the neighbors. Is it possible that this becomes imperfect? We will show that it is not possible, it is always perfect. Now, to do this thing, so we will, to prove that a graph is perfect, it is not just enough to show that chi is equal to omega for the entire graph, we also have to prove the statement for all the induced subgraph. Now, but now here if you look any induced subgraph, it is either completely coming from here, right. So, or see it can be something like this, in which case we know this graph itself was perfect, any subgraph of its it's also perfect, or otherwise it can contain two of these things and then it can be something like this, in which case, but then you will be leaving out some other vertex here. So, it is a this being a smaller graph than G, this being a smaller graph than G. So, it is like you have expanded x in the smaller graph, and therefore, for all smaller graph this expansion we know that if you expand a vertex, the perfection will not be lost. That is the induction hypothesis. Therefore, we know that so that induced subgraph also will be perfect. Again I repeat, so we have to verify that the chi equal to omega property is satisfied not only for the entire graph, but also for the all the induced subgraphs. So, we will claim that in fact we can discard the proper induced subgraphs. I mean we can concentrate on the entire graph only, because suppose it was an induced subgraph which is strictly smaller than the entire graph, then that induced subgraph is either a subgraph of G, this original graph, in which case it is perfect by definition, because the perfect graphs, an induced subgraph of a perfect graph is also perfect, or it contains x as well as x dash, and some other vertex is left out from the original G. Original G was this is this, the entire this G dash, this is G, this violet is G, and this entire thing is G dash. Right. Now you know that some smaller graph of G was selected and the vertex x in it was expanded to x dash. That is how we got this kind of an induced subgraph. That is why it is perfect by induction, because for all smaller number of vertices we had already assumed the result is true, right. So, it is also perfect. You may ask, what if x is not there, only x dash is there, but it does not matter, because it is as good as it is isomorphic to a graph where x is contained and x dash is not contained. So, it is just another I mean instead of x you can take x dash. So, that belongs to the former case. So, therefore, so our point is that we need not worry about all induced subgraphs of G, because all induced subgraph of G are automatically taken care of by the induction assumption, or because it is a subgraph of G. Now, we will consider the entire graph G dash only. We want to prove that omega of G dash is equal to chi of G dash. How will you do this thing? So, this is the G, and here we have this x, and here we have this x dash. So, this some neighbors are here and some neighbors are here. So, this is the situation. Now, the question, so what we are bothered about here is what is the chromatic number of it, what is the omega of this, right. Now, the first point is, when you expand it, is it possible that the omega increased? Is it possible that the omega increased? When you expand it, is it possible that the omega increased? If the omega increased, that means the clique number increased by 1, then we only have to show that we can color the entire G dash with one more color than which was needed for G, right, because the chi of G, we know that for G is a perfect graph, omega of G equal to chi of G, therefore, and then this became plus 1 for omega G dash, right. Now, here also we have one more color available, we can color it, we can use that extra color to color the new vertex, and therefore, it is of course our omega of G dash and chi of G dash will be equal, because an extra color will be available because the omega increased, right. You retain the coloring of this, the omega coloring of this thing, and then use the new color. So, we can assume that by expanding, the clique number does not increase, that means the maximum clique remains omega. Now, but we have added one more vertex. Though G was colorable using omega colors, is it possible that after expansion we may need one more color? This is the question, right. Now, if it happens, so if it happens, what can I tell? So, I have assumed that omega is not increasing. If omega is not increasing, what can I tell about x and a maximum clique? So, you take any maximum clique, is it possible that x is present in that maximum clique? Suppose this was a maximum clique and suppose x was present in that means it is a neighbor of all the other vertices in the clique, right. Now, if you introduce x dash and you make this adjacent to all the vertices here, now you of course there will be a new clique containing this entire thing and the newly added x dash, right. So, it means that our clique number will go up. So, it means that x was a vertex which was not part of any maximum clique in G, right. X was always outside any maximum clique. But on the other hand, if you consider a coloring of G, omega coloring, we know that there is omega coloring of G, there is an omega coloring of G since chi of G equal to omega, right, because G is a perfect graph by assumption and chi of G has to be equal to omega. So, there is an omega coloring of G. Now, in this omega coloring, x is also in a color class. So, let us say x belong to a color class, say we can say, so for the sake of C is the color class where x belongs to, right. C may be the color class in which x is part of, or it can be a say this green color class. Maybe I will identify in the graph, I can identify the green color class. So, see x belongs to the green color class. So, this x may be here, x may be this, but then interestingly x does not belong to any maximum clique. But then if you consider any maximum clique of G, because it contains omega vertices and each of the vertex has to get a different color, there should be a representative vertex in each maximum clique for each color. That means, if you take any color in the omega coloring, there should be one vertex in the maximum clique having that color, because the maximum clique has omega vertices, each of them should get different colors. So, they should take up all the colors. So, for every color there should be a representative in a given maximum clique. So, in particular this green color class also should have representatives in each maximum clique, but then we know that x is not such a representative for any maximum clique, because x does not belong to any maximum clique. So, these remaining gays, this is C minus x, right. These remaining green vertices will intersect with each maximum clique. That means, there is a representative from this collection, this C minus x in each. Now, what will happen if I remove this collection of vertices, this green vertices other than x from the graph? That means, every maximum clique will reduce its size by 1. So, after removal of this set, the new graph, say let me call it a G double dash, this omega will be omega minus 1. Now, G double dash is a subset of the original graph G, therefore, it is a perfect graph, therefore, its chromatic number also has reduced to chi G minus 1, right, because the clique number is omega minus 1, the original coloring number was omega. So, it should become one less now, okay. It can be colored with one less color. So, one color we have free. Now, you know that this color we removed, this is an independent set. Now, x is already there because we removed only this thing other than x, but we have this x dash instead of x, we can add it into this collection, because x is not adjacent to any of these gays. So, x dash also will not be adjacent to any of these gays. So, together with x dash, so that means this plus x dash will be an independent set, right, this plus x dash will be an independent set. So, now we can add this new independent set to the vertex with just one more color, because all of them need only one color, because that is an independent set, you can add it. So, therefore, this plus one more color will be enough to color the entire graph G dash. Chi of G dash will be equal to omega, right. So, therefore, we after expansion whichever graph was there we colored with omega colors. So, this completes the proof that after expansion the perfectness will not be lost. So, the sequence of arguments was that. So, you first noted that if you are expanding a vertex x to an x dash by introducing a new vertex x dash, then to establish the perfectness of the new graph, that means expanded graph, you only have to prove that chi is equal to omega for this new graph, big graph, because any induced subgraph will be either an induced subgraph or isomorphic to an induced subgraph of the original graph G, or it will be obtained from a proper induced subgraph of G by expanding the vertex x, right. So, therefore, in both cases we can apply either the fact that G is perfect or the induction hypothesis to assume that the induced subgraph satisfies the property chi equal to omega, they are perfect anyway by assumption. Now, we only have to establish omega is equal to chi. Now, we considered two cases. First case was easy. Suppose after the expansion the clique number increases. If the clique number increases, the chromatic number also can increase by 1. So, we have enough colors to accommodate the new vertex. So, we can assume that the clique number does not increase. So, if the clique number does not increase, then the key property is that x cannot belong to any maximum clique in the graph G. That is a good thing, because the color class C of x, when you consider an omega coloring of G, will have to cut all the maximum cliques, but a representative from this color class to a maximum clique can never be x. So, you can rather leave x in the graph and remove the remaining vertices of that color class. It is an independent set, you do not remove the entire color class, you leave the x there in the graph as such, remove the remaining things. Now, the graph has become a smaller subgraph of S, subgraph of G, it is a perfect graph. So, but the key point is you manage to bring down the size of the maximum clique from omega to omega minus 1, because one representative was removed from each maximum clique. The good thing was that representative was not x. So, therefore, we could leave x there itself without removing. So, now because the maximum clique size is omega minus 1, so you just need omega minus 1 colors to color. Now, we have one more color if you want to color using omega the entire expanded graph. Now, we can give back whatever we removed, that was an independent set. Not only that, that x dash new vertex after which we used to expand x, x dash, that also can be added, because x dash behaves like x, and if x dash is added along with this color class, it will not become not independent, it will also become an independent set. So, together with x, that whatever we removed from the graph can be added back, but with one color, because it is an independent set, only one color is required. So, with omega colors we can color the entire graph, this is the idea. So, therefore, we managed to prove that in both the cases chi is equal to omega for the so, therefore, it is a perfect graph. So, this is a lemma which we will require later. Now, we will come to the proof. So, suppose again it is an induction proof, we assume proof of what? Proof that if G is a perfect graph and then the complement is also going to be a perfect graph. To prove this, we will again use induction. So, for one vertex graphs it is obvious, because if you look at the complement, what is that? It is the same graph. and or if 2 vertex graphs, you can take all combinations and check whether if it is perfect, its complement is also perfect or not. It is, right. It's very easy things. So, therefore, let us assume that all smaller graphs it is known, and we take the new n, right, for which we have to prove. It's a G is a perfect graph. Any subgraph of G is known to be to satisfy the statement also it is perfect, therefore, its complement is also perfect. Now, to show that our intention is to show that G complement is perfect. So, to show that G complement is perfect, you have to show that every induced subgraph of it also satisfies the chi equal to omega property, but then we again notice that it is not very important, because if you take a proper induced subgraph of G complement, that is the complement of some proper induced subgraph of G, right, and then their induction hypothesis is already valid, because that is a smaller number of vertices there. Therefore, induction hypothesis is already valid, that means any perfect graph should satisfy the fact that its complement is also perfect. G's induced subgraphs are perfect, therefore, its complement is also perfect. So, any proper induced subgraph of G complement is perfect, satisfies the chi equal to omega property. Therefore, we only need to bother about this entire G complement, we have to show that its chi is equal to its omega, and now we will work on G rather than working on G complement. So, that means we have to prove that this chi will become the clique cover number in G, right, clique cover number in G. And yeah, the clique cover number in G, and the omega of G bar will become the alpha of G, this we know, right, alpha of G. So, now the point is to show that we have a clique cover of G using exactly alpha of G number of cliques. Now, so the key point to note is that suppose you have one clique in G, suppose you have one clique in G, K in G, such that K does not intersect with so one clique in G such that K intersect with all the K intersect with all the maximum independent sets of G. Then what does it mean? So, that means that if you remove that clique from G, the maximum independent set size itself will reduce. If you have one such clique which will intersect with each maximum independent set, then when we remove this clique from G, the maximum independent set size cardinality itself will reduce, alpha will reduce to alpha minus 1. Now, the smaller graphs are satisfying already the perfectness property, because the smaller graph is already perfect. So, its complement also have to be perfect by induction hypothesis. So, there we will get the fact that alpha is equal to clique cover number. So, you will get a collection of cliques which will cover the entire the alpha minus 1 cliques which will cover the entire graph, or in other words in the complement we will be able to color using alpha minus 1 colors. The complement can be colored using alpha minus 1 colors. Now, you have only removed one clique, you can reintroduce the clique to the graph with one extra. So, alpha minus 1 will become alpha, the clique cover number will be alpha even for the entire graph. So, that will work, or in other words in the case in terms of the complement, we are saying that this clique is introduced in G means an alpha is introduced, an independent set is introduced in the complement. So, we can color it with one extra color. So, alpha minus 1 coloring was available. So, with alpha colors we can manage the entire complement, alpha being the clique number of the complement, that alpha is the independence number of the original graph G, right. So, the point here is that this statement is enough to complete our proof. That means, if you can find out one clique in G which can intersect with all maximum independent sets of G, then we are done, because we remove that clique from the graph. So, we got a smaller perfect graph, because G is a smaller perfect graph, G is a perfect graph, and after removing K we will get a smaller perfect graph, an induced subgraph of G is perfect. Not only that, induction hypothesis can be applied now for the smaller case. That means, in the complement we get a perfect graph, the complement of the smaller graph will be a perfect graph. That means, there the chromatic number and clique number will be equal, which means that here alpha equal to clique over now, alpha the independent set number is equal to the clique number. Good thing is, independent set number reduced by 1. In other words, if you can so if this can be covered with alpha minus 1 cliques, since one more clique is added back, so alpha cliques are enough to cover the entire thing. This is the point. So, somehow rather easy argument, in fact, that point, if this works, then our proof is done, but then that this works, what we are asking for is too much. In fact, we are saying that we want to find one clique which will intersect with every independent set of G, every maximum independent set of G. Why should it intersect with every maximum independent set of G? Is it possible? Because there can be several maximum independent sets of G. How can you somehow adjust one clique to cut with all maximum independent sets of G? So, it looks like a little too much of a demand that you are making, but it so happens that it is true. Because it is true, then our proof is done, right. So, why is it true? That is the only thing we have to verify now. So, now to prove that such a clique exists in G, what we will do is to assume that suppose such a clique does not exist in G. So, we will collect all the cliques of G. So, that means we will say K1, K2, K3, this is the set of all cliques of G, right. So, there can be several cliques, so all the cliques are collected. Now, you know that you take K1, you know that this clique is such that it cannot cut all the independent sets of G. If there is a maximum independent set, right, there exists a maximum independent set S1 corresponding to K1. See, look, S1 cardinality is equal to alpha, it is a maximum independent set. Moreover, this K1 intersection S1 will be empty, because you can find one S1, because there should be at least one maximum independent set which it cannot cut, right. Similarly, for K2 also there should be one S2 such that it does not intersect with it, right. So, here we are taking S, so for each Si, so for each Ki you can associate a Si such that it is a maximum independent set, that means its cardinality is equal to alpha, and also Ki intersection Si is equal to phi, right, it does not intersect with it. This is the point. Okay. So, it means that with each Ki I can associate a maximum independent set Si such that Si does not intersect with this Ki. This is suppose this happens, we will show that there is a contradiction. What is the contradiction? This is what we are going to do is, we will take up each, so we are going to expand G, we will take G, we will take up any vertex x, right, of G. Now, we will see in how many of these Si's we can write down this S1, S2, S3 corresponding to each clique, we have this K1 corresponding to S1, K2, we have this see they some of them may be same, but it does not matter, we will consider different copies of that. And so suppose this x, it may be part of this, it may not be part of this, it may be part of this, right, some S4, and it may not be part of S2 and S3, it may be part of S10. So, we will count in how many S i's it comes. Suppose it comes, x comes say 20 times, then what will I do? I will make 20 copies of x here, and total including this original x, total 20 copies, and I will replace this x with a clique of cardinality 20, and each vertex of this clique will have like x in terms of its adjacency. For instance, to which all neighbors x is adjacent, they all will be adjacent. To a non neighbor of x, none of them will be adjacent. So, it is as if x has multiplied it into 20 copies, right, of itself. So, it is x friends are all the friends of the neighbors of x are the neighbors of all the vertices in the clique, the non neighbors and not the neighbors of any of these vertices in this clique. You can see that such a clique can be obtained by repeated expansion operation. You can keep on expanding it 20 times, sorry 19 times, right. So, then it will bring that entire clique. So, you can do it for every vertex one by one. So, that will get us a graph which is much bigger than the original one, but we are replacing every x by so many copies, that is all, and then between the copies you are making a clique. And of course, this entire graph can be obtained by repeated expanding, right. You select the correct vertex and expand it, select the correct vertex and expand it, is not it. Now, the good thing about this graph is because we obtained it by expanding operation, a series of expansion operation from G was a perfect graph to begin with. So, this new graph is also perfect graph, right, the new graph is also perfect graph. So, we can call it G dash. So, from G we obtained a G dash. So, since G is perfect, G dash is also perfect, because the way we obtain G dash is by expanding vertex after vertex several times sometimes. Now, it is even possible that some vertex may become extinct from the graph, because go away from the graph, can be removed from the graph, because that vertex does not appear in any of these things. So, the number will be 0. So, it is like we remove it. So, that means we are essentially we are expanding subgraph of G and getting all these things, not necessarily G, because some vertex may disappear also, right. So, now we have G dash a perfect graph. So, about G dash what I can say is, because it is perfect graph, chi of G dash has to be less than or equal to omega of G dash. You remember, its chi of G dash can never be strictly less than omega of G dash, because chi of G dash, which means that this is equal to omega of G dash, right, because for the perfect graph we can as well put it as equal to. Now, we will show that by counting in a different way, we can show that this is wrong, a contradiction we can show, or in other words, by counting in a different way, we will show that chi of G dash has to be strictly greater than omega of G dash, which will be a contradiction, right. It will be a contradiction, because how can G dash be perfect in that case? See, the key observation is to count both. I mean, so let us see how much is omega of G dash. See, this omega of G dash is essentially a clique of G dash. You remember, to construct G dash from G, what we did is we replaced each vertex with a clique having so many copies of the corresponding vertex, and made whenever two vertices x and y were adjacent in the original graph, we may put all the edges between them, right, that is the expansion operation, right. So, therefore, if you had selected a clique of the original graph G, and when you expanded all the vertices in the clique, we will get a big clique, right. and it is easy to see that any big clique, any clique which in G dash is obtained from G like that by selecting some clique and expanding, right. So, therefore, we can say that this omega of G dash, so the biggest clique will correspond to some clique, say x of G, such that the number of vertices is omega of G dash is equal to sigma of x element of x, how many times it was multiplied, right. We can say how many times it is multiplied, right. So, we can put say h of x is the multiplicity of that x. Now, we know what is this? This is essentially this clique vertices will be, you know what, for every vertex, for instance if I write x equal to x1, x2, xt, then x1, if you remember the way it was counted, this x1, suppose this was a clique. So, x1, x2, x3, this clique, this counts in which all these things I am part of. See, one point we can notice that suppose x1 is part of S1, then x2 cannot be part of S1. Why? Because S1 is an independent set, here it is a clique. So, this clique only one vertex can be part of S1. So, suppose, so you can think that these S1, S2, X3 etc. are counting the total multiplicity due to this clique. So, that is the sum of h of x1 plus h of x2 plus h of x3 if it is to be counted from the point of view of these sets, right, S1, S2, S3 etc. S1 will say that I will anyway count 1 or 0 for that this entire clique, because only one vertex from this clique can be inside me, right. Because if they are counting, no two of them will count me, only one guy will count. Therefore, this S1, from S1 you may get 0 or 1. So, from S2 also the same thing, 0 or 1 it may get the total count for this entire thing. So, this entire counting, the entire sum is contributed by S1 either 0 or 1, maximum 1. So, the maximum contribution can be total, this cardinality of this the total number of these things, that means the total cliques, that means can be if k is the total collection of cliques, it can be k. But then there exists one among these sets which does not contribute, which is that, because we know every clique is such that it has a pair, because this clique itself, if this clique is called say kt, kt will be appearing somewhere here and it will have an st, right, such that their intersection between them is 0, that at least that st would have counted 0 for it. So, that guy would not contribute, that subset would not, that independent set would not contribute to the count. So, we will only get k minus 1, because all these cliques will not contribute, all of them can contribute at most 1, and there exists one among them who will not contribute. So, k minus 1 is the maximum. So, we can say that this number is in fact k minus 1, where k, this k is the collection of the entire collection of the full collection of cliques, the set of all cliques in G, right, k minus 1, is not it. So, then now, so we got an upper bound for omega of G dash. Now, we will show that chi of G dash is strictly bigger than that. We will show that chi of G dash will be bigger than or equal to k. So, which will be definitely strictly bigger than k minus 1, that is which is greater than or equal to omega of G. So, which is a contradiction for our this thing, because we want to we knew that because it is a perfect graph, this is correct, right, chi has to be equal to, chi of G dash has to be equal to this thing, and but it so happens that this turns out to be true, because this is only k minus 1, and we will show that this is at least k. So, that is strictly bigger. So, how do I show that this chromatic number is at least k? To show that the chromatic number is at least k, usually the chromatic number is because to show a lower bound for chromatic number, what we do is we will divide the total number of vertices So, that means n of g dash, the total number of vertices. So, let us say, or we can just use this notation, g dash, the total number of vertices divided by the maximum independent set size of g dash, right. This is enough. In fact, because you see, because this can never be lower than this, because this color class, each color class can contain at most this, right. So, therefore, you need at least g by omega d dash, this thing. But interestingly, this omega of g dash can only reduce, because our operation was to substitute each vertex by a clique. Now, your omega cannot increase, because the original biggest independent set can be only bigger than or equal to this omega of this, sorry, this alpha of this thing. So, this can independent set size cannot increase if we replace each vertex of the graph by a clique, right, because any two of the same clique cannot participate in independent set. So, essentially it is the original independent set only, right, or therefore, we can say that chi of g dash is less than or equal to omega. So, instead of this thing we can just put alpha, original alpha, right, original alpha. Now, how much is g dash? So, how much is the, so we know that chi is greater than or equal to the cardinality of g dash, the number of vertices in g dash divided by alpha. Now, how much is g dash? G dash is essentially the sum of, g dash is essentially the sum of all vertices in V of g, right. So, how much is the multiplicity, because every vertex was substituted by an h of x size clique, the multiplicity, so many copies of x, right. So, this you just have to sum up the multiplicities. Now, again going back to this picture, how this multiplicity, if I want to sum up the multiplicities, yeah, if we want to sum up the multiplicities, so we can see that that's the sum is essentially, because the total, see, for again we can ask, we can count from the side of S1, because how much S1 will contribute to the total sum of multiplicities. S1 can only contribute the total cardinality of it, right, because in the S1 every vertex may count, because every vertex in S1 will count once that S1, right, not more, not twice. The same vertex will not count S1 two times. So, all the vertices in S1 will count it once. So, therefore, S1 will contribute total its cardinality, that namely alpha. S1 will contribute an alpha to the total count. So, S2 also will contribute an alpha to this thing. So, similarly, so therefore, we can say that the total the contribution will be equal to alpha times k, isn't it? Why? Because if you want to find out this total sum, you ask each of the size, that S1, S2, S3, etc., how much you have contributed to the total sum, because one SI will say I have contributed alpha, because its cardinality is alpha, because for each vertex inside it, it will contribute 1. So, alpha, it will, total contribution will be alpha from each side. Since kappa sets are there, total contribution will be, sorry, not kappa, sorry, k sets are there. So, this many sets are there, k into alpha. So, this can be substituted by k into alpha, right. So, cancelling this alpha and alpha, we get chromatic number has to be at least the number of cliques in the graph. So, chi is greater than or equal to k. So, we see that chi is greater than or equal to k, omega is less than equal to k minus 1. So, chi is strictly greater than omega. So, we have shown that this is not a perfect graph g dash, but g dash has to be a perfect graph, because g dash is obtained from a perfect graph g by expanding vertices one by one, right, repeated expansion of vertices, right. So, it has to be a perfect graph. So, this is a contradiction finally. So, what do we infer from that? What is it contradicting? Essentially, the contradiction came from the fact that we did not have any clique in the graph which intersect with every independent maximum independent set of the graph G, because if there was even one, then in this calculation we would not have got the contradiction, because we saw that the total sum every clique contributed 1 at most, and there was one clique which did not contribute, right. So, because that was possible because every clique could identify one maximum independence which is not intersecting with it. So, this contradiction came from that. Therefore, we can infer that there exists a clique in the graph which will intersect with every maximum independent set of the graph. Now, the proof is obvious, you just remove that maximum clique. Now, the remaining graph satisfies the induction hypothesis, that means the complement can be colored with alpha minus 1 number of colors. Now, put back this clique, that means in the complement there is one big independent set is added. So, one more color is necessary. So, k colors alpha colors are enough to color the entire thing. So, this finishes the proof. In the next class we will consider a different proof of this thing by this weak perfect graph theorem by a person called Gasparian. So, the original proof is by Lavash, right. We will that proof is a little shorter, and we will consider that. Thank you.